Hello and good morning, dear children. Welcome to Vista's Learning, an online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we'll discuss a physical quantity that is called an acceleration. This is a session 2 of the chapter Motion in a Plane. In the previous chapter, we came across the same physical quantity, acceleration, and we defined this physical quantity as the rate of change in velocity. Its unit, meter per second square. So how different is this from the previous chapter? The previous chapter, we discussed acceleration along a straight path. But in this chapter, we shall discuss acceleration in a plane. And when I use the word plane, it means a two-dimensional surface, which have the respective reference coordinates as x-axis and the y-axis. So let's dive into our session. With a quick recap from the previous session, where we discussed what is velocity, how we define velocity in a two-dimensional plane by a graphical method, also by an analytical method. So here is one graph which defines a type of velocity called instantaneous velocity. OPR represents the position vector, and this the other vector, let's call it delta R vector, is your displacement vector. We also determined that the direction of the velocity is in the same direction of the displacement vector. So this delta R and the direction of V could be matched and they would be the same. Now, we also discuss a few components of velocity, namely the x component and the y component, such as this. For a given vector, which is represented in this case as a velocity, you have the x component given by Vx and the y component given by Vy. We derive this x component and y component using set of position vector and also a displacement vector. But now we will notice how this x component of a velocity is related to the vector v. Also, how the y component of velocity is related to the vector v. Shall we get started? All right. So first, you see that you have a right angle triangle with an angle of inclination, that is theta. To identify the component of x, v of x with respect to v, we choose a trigonometry ratio. A trigonometry ratio that gives you base and hypotenuse. Base by hypotenuse. Which trigonometry ratio is that? Cos theta. Cos theta is equals to base, which is v of x, divided by the hypotenuse v. So we write v of x equals to v cos theta. So you see the relation between v of x with the vector v, which is equals to v cos theta. So in place of v of x, you can substitute it with v cos theta. Similarly, what can you equate this v of y, or how is it related to the vector v? Again, you can choose a trigonometry ratio such as the opposite by the hypotenuse, which is sine theta. So sine theta equals to opposite is vy, hypotenuse is v. Therefore, Vy equals to V sine theta. So this particular y component can be replaced with v sine theta. So I hope I've made this clear, how a given x component and the y component are related to a given vector v. So why is it necessary for discussion? Since we are discussing the concept based on acceleration, which is nothing but the rate of change of a velocity, it is important for us to understand the velocity. Now that we know that the velocity have two respective components, which is v of x I cap plus v of y j cap, the rate of change of this velocity is represented by delta v by delta t. Remember, when you use the word rate of change of some physical quantity, it is always with respect to time. So the rate of change of velocity in this case gives you acceleration. Now, what do we know about v? V is v of x I cap and v of y j cap. So I substitute in place of v as delta vx I cap plus vy j cap divided by delta t. So this delta is the difference. So this difference can be used along the x-axis as well as along the y-axis. So the difference can be observed on both the reference axis, namely the x-axis, as well as the difference in the y-axis, divided by delta t. Now that you have the LCM, which is delta t, these two terms will have the same denominator, which is delta t. So I will separate the terms as delta v of x I cap by delta t plus delta v of y by delta t j cap. I'll choose a different color now. So this is how you define an acceleration. The type of acceleration is what we call as an average acceleration, represented by a and a bar overhead. Okay, so this type of acceleration is called average acceleration. Delta Vx by delta t, rate of change of velocity along the x-axis. How much the velocity changes only along the x-axis. So if the velocity is changing only along the x-axis, then the acceleration will also be along the x-axis. So you have a bar, which is equals to a of x I cap, because this component represents the change in velocity along the x-axis. Similarly, rate of change of velocity along the y-axis. How do you know if it's y-axis? Notice here, we have put y component for velocity. So rate of change of velocity along the y-axis, meaning if there's a rate of change in velocity along the y-axis, then the acceleration will also be along the y-axis. Therefore, a of y j cap. So this is how you define an average acceleration, where you have the x component of acceleration as well as the y component of acceleration. So let's look at the quick definition of this. I'll erase the remaining. This we already know. This, I hope you have written it down. The average acceleration of an object, okay, of average acceleration a bar, you put a bar, of an object for a time interval delta t moving in xy plane is the change in velocity divided by the time interval. So we have noticed here is the change in velocity divided by the time interval. And that can be equated to this, where the average acceleration can be split into two respective components as x component and the y component. So now that we have the average acceleration in this form, can we find its magnitude? Certainly, why not? To find its magnitude is very simple task, where acceleration, magnitude of an acceleration, which is equals to square root of ax square plus ay square. Now what about its direction? Again, for direction, we use tan theta is equals to ay by ax. Now that we just have a formula for direction, how do you graphically represent it? Now that is what we're going to discuss in the next section, is how to graphically represent an acceleration. So for that, I would take my two reference axes, all right? You have the x-axis as well as the y-axis. Call it the x and the y-axis, all right? Consider an object that displaces from one position to another, and a path taken looks something like this. So this is what is called as an initial position. This is what is called as a final position. To identify these positions, you construct a position vector. So a position vector which is drawn from the origin, let's say O, to point P, and to this new point which is P prime. For the sake of simplicity, we call it R1 and R2 vectors. So R1 vector, R2 vector represents the position vector. The velocity at any given instant of time at point R1, or the instantaneous velocity at point R1, how do we construct? Is by using a tangent. To find the instantaneous velocity, we use tangent. So you draw a tangent to the given path from a position vector. Let's call this V1. V1 represents the instantaneous velocity at position R1. Similarly, V2 will be the instantaneous velocity at position which is P prime. Here I said R1, sorry, it's P, all right? So V2. So now you have two vectors, which is of V1 and V2, okay, velocity. Now we define acceleration, again, we define acceleration as the rate of change in velocity. Now this is happening at a given instant of time, so nothing to worry about the time. We take these two velocity components, these two vectors, put them together. So one vector is represented in that direction, the other vector is represented in that direction. Okay, these two are vectors. Now in which direction will be the acceleration? Remember, again, acceleration is the rate of change of velocity. In which direction is the velocity changing? Path is from P to P prime. P to P prime. So the object, since it's displacing from P to P prime, then the velocity is changing from V1 to V2. So the direction of acceleration will be in this downward direction. So acceleration in a graphical method can be identified by drawing a vector from initial vector to that final vector. So this is nothing but delta v by delta v, or we'll write it a because since it's instantaneous velocity, so we'll just represent it with a vector. This would be the direction of a vector. So let's take a look at more example how this direction can be identified. And here are a couple of diagrams where acceleration, the direction of the acceleration is identified. So here you have instantaneous velocity at point P, instantaneous velocity at point V prime. The two are put together. The difference between the two, the path, you see delta V, the path delta V pointing this way will be the same direction, which will be acceleration. Acceleration will be the same direction as that of a delta V. So the arrow is drawn such a manner, the change takes place from an initial velocity to a final velocity, initial to a final. Similarly, moving on to the two, initial velocity, final velocity, delta V. So as you look one after the other, you notice the path delta V is becoming shorter and shorter, right? So now delta V is shorter here, it is shorter at this point, and eventually delta V vanishes. What has happened here that delta V vanishes? So we are trying to determine in this particular graph, we are trying to determine acceleration at that given instant of time. To determine this acceleration at that given instant of time, we will soon have a look at it, but the type of acceleration is what is called as an instantaneous acceleration. So it is the limiting value of average acceleration as the time interval approaches 0. So what exactly does it mean for a time interval to be approaching 0? Let's take the case where a limit is applied, where delta t tending to 0 is applied to the rate of change of velocity, which could be said as an average acceleration. So to the average acceleration, you're applying a limit. Now v, as we know, is v equals to vxi cap plus vy j cap. So limit delta t tending to 0, delta vxi cap plus vy j cap divided by delta t. Now we have already looked into this form in the previous section, so I will directly write the solution separating the LCM and things like that. So where you get limit delta t tending to 0, delta vx I cap divided by delta t plus, you apply limits to delta y as well, both the terms. Y is because this is also a function of time, vy, because it has the same LCM, delta vy divided by delta t j cap. J cap. Sorry. J cap, all right. So put that as a j cap form. Once you solve this, limit as delta t tending to 0, delta vx by delta t is the instantaneous velocity along the x-axis. Sorry, instantaneous acceleration, why am I saying velocity? Instantaneous acceleration along the x-axis, meaning acceleration that takes place at a given instant of time. So ax I cap plus, similarly you have ay j cap, which is instantaneous acceleration along the y-axis. So that would give you the value for an instantaneous acceleration. These are all vectors. Now, in fact, this component AX is quite related to limit as delta t tending to 0, delta Vx by delta t. Now, this is too big to write. I know though it takes small space, but still consumes time to write. So the easy way to define this is by using differential calculus, which is dv by dt, but v of x. The component is along the x-axis. So ax can be written as dvx by dt. Similarly, ay can be written as dvy by dt in its respective differential equation form. So this is how you can identify instantaneous acceleration. So there are two types of acceleration, the two different types of acceleration that we have discussed. One is called the average acceleration. We looked at it by an analytical method, also by a graphical method, and now instantaneous acceleration, we looked at it by a graphical method and by an analytical method, where we derive this following term, where you have the x component and the y component of an instantaneous acceleration. So what better way to understand this by solving a problem? So let us go ahead and solve a problem based on this so that we get a better idea of what we're dealing with. Question: the position particle is given by r equals to 3t I cap, 2t square j cap, 4 k cap, where t is in seconds, and the coefficients have the proper units r to be in meters. Find velocity v of t, a of t of the particle. Find the magnitude and direction of v of t at t equals to 2 seconds. So we need to find what will be the velocity as well as the acceleration. This is actually a question from your NCERT textbook, from your exercise problem. So one of the exercise problem is this. So we'll go ahead and start solving them. You've been given the position vector, and now you need to find v of t and a of t. To find v of t, you have to differentiate that position vector, which I will do it for you. So you have 3t, so it becomes 3 I cap. So I'm trying to write the answer directly. I will avoid doing that. I will guide you step by step. d by dt of 3.0 t I cap plus, no, it's minus 2.0 t square j cap plus 4.0 k cap. Okay, now we need to differentiate the following equation. Go ahead and try this with me. So you get 3.0 I cap minus 4.0 j cap, and then differentiation of just a constant is 0. Oh, there's one t that I've left out. I've left out the t, so make sure you use the t here. Okay, it should be 4.0 t j cap. T j cap. All right, so this would be the velocity of an object. We have found one part of it. We also need to find the acceleration. So let's find the acceleration. Acceleration is the rate of change of velocity, which is dv by dt. Do we know what is v? Yes, we do. So we substitute 3.0 I cap minus 4.0 t j cap. Now we differentiate it. So I'll move it here, where acceleration a of t which is equals to, once you differentiate this, this is just a constant, so this will be 0 minus 4 minus 4.0 j cap. I'm not going to mention the j cap as well, so I'll just write minus 4.0 meter per second square. So this will be the solution for acceleration, which is minus 4.0 meter per second square. Minus represents the direction, so we already have the direction. So this would be along, first of all, this would be along the y-axis, because remember the unit vector is along the j cap. So this would be along y-axis, but since it is negative, along minus y-axis. So which means it will be downward direction. All right, along minus y-axis. Right, now the next part is find the magnitude and direction of v of t. So now you have v, find the magnitude when time t is equals to 2 seconds. So first we write that v of t is equals to 3.0 I cap plus 4.0 t j cap, and when you substitute 2 in place of t, you get 3.0 I cap plus 4 times 2 is 8.0 j cap. Next, we have to find the magnitude. Magnitude of v is equals to square root of 3 square plus the 8 square, which is equals to 9 plus 64. Okay, so which is equals to 73. So go ahead, try to identify what is the square root of 73 meter per second. All right, next, direction. Tan theta is equals to y by x, which is 8 by 3. Tan theta, which is equals to 8 by 3. Okay, 2 times 0.3226636 times is 18, 6 bar, we get 6, 7. Let's put 6, 7. So theta will be tan inverse of 2.667. That will be the direction, and this will be the magnitude of the given vector. So I see I've filled every single inch of the board. Good sign. So that is all I have for today. Do visit us at www.v-learning.in to get more details about the classes. The next session we will discuss concepts that are based on parabolic motion, objects that move in a parabolic path, which is also called as a projectile motion. So we will discuss those in the next class. Stay tuned. Take care everyone and have a nice day. Bye bye.